I'm Mohammed Billoo, part of MAB Lab's Embedded Solutions, and we're going to talk about Zephyr and OpenAMP. And if you listen to my last two talks at FOSDEM and then last year's Zephyr Dev Summit, like a lot of these talks have been motivated by me being in close proximity to FPGA engineers. And so, this is the next iteration in that sort of kind of development process. I try to claim to be an FPGA engineer, but I still stick to the embedded software side. So just a quick agenda for today's talk. We're going to go over motivation behind what we're doing. We're going to talk a little bit about the OpenAMP overall framework and its relation to Zephyr. The system architecture for the project that I worked on, I had to change some things because it was a client-based project, but the overall kind of framework and structure was similar. So we're going to talk about what that looked like, the development process, and this is not a Yocto class, but just because of the nature of the project that I worked on, like there were some Yocto bits, so we're kind of go over that in a slide or so. Some common issues and like the resolutions that I discovered. So if you're also doing something with OpenAMP, that could be useful for you, and then kind of next steps to wrap it up. So just a little bit about myself. I'm an embedded software consultant. So I do a lot of design work that includes all sorts of verticals from medical devices to custom ASICs, which is the motivation behind a lot of the talks that I've been doing with FPGAs. If you know anything about ASIC development, the first thing you generally do is prototype it on an FPGA. So a lot of my clients recently are like, hey, this Zephyr thing is cool. We've been doing all of this stuff in FreeRTOS. Can we try to do things with Zephyr? So a lot of this has been some relatively new things that I've been working on. And it's been the motivation for these talks. You can follow and connect with me on my social media accounts that are listed down below. And then I have a newsletter that I distribute on a monthly basis. So if you want to sign up for it, you're welcome to, and you can find that on my website as well. So just a quick kind of summary about the motivation behind OpenAMP. So we have nowadays a lot of heterogeneous multiprocessor systems, and traditionally they have been on distinct silicon dice. So if you take the example of, let's say, a car, the automotive industry, you have different MCUs that are responsible for different kind of real-time subsystems. So you have an MCU that's responsible for brakes. You have an MCU, or they call it an ECU, responsible for like the shocks and suspensions, et cetera. And then so they all communicate using like some common buses. So in the automotive industry, that's the CAN bus. We can use UART, we can use SPI or I2C. So a lot of these different controllers, let's say microcontrollers, they communicate over these kind of distinct buses. And so in addition to an MCU that's responsible for some of the real-time components, you have an MPU that doesn't have any real-time requirements, but it's responsible, for example, in the automotive industry for the infotainment system. And again, they all have to kind of communicate over these pretty popular, these common buses. But recently, right, the silicon, as we all know, silicon density has exploded pretty substantially. So you don't have like a single CPU or a single controller on the silicon itself. You actually have a lot more hardware that's stacked on an SoC, right? So this is an example of an NRF52840 SoC, and we can see that they have a radio subsystem, right? Hardware to implement a radio subsystem, USB, all sorts of peripherals, and et cetera. And we can see that actually the core itself constitutes probably the least, one of the fewer in terms of silicon area. So nowadays we have a lot more going on in our SoCs beyond just the CPU itself. So what as kind of an extension to that is we can add, like a lot more silicon vendors now are adding microcontrollers and microprocessors onto a single die itself. So, we have an extension here where it's like, okay, you have different peripherals on the die itself, but now you're adding multiple cores and multiple controllers themselves also on the SoC. So the advantage of that is we can kind of distribute the workload of our application across the different microcontrollers and also even multiple MPUs as well. So for example, like if you have an MCU, that can be responsible for a lot of the real-time operations, going back to kind of like the automotive space, the actual components that are responsible to make sure that are safety critical. And then the MPU can be responsible for some of the non-real-time components. Another application for this is robotics, where you have, again, like the MCU responsible for actuation, and then the MPU can be responsible for like the GUI, display communication, things that are not real-time or safety critical components. So for example, now, if we look at an SoC that's relatively modern, and actually pretty modern and new, is we can see that we have multiple MCU cores or different types of cores and heterogeneous subsystems within a particular silicon itself. So you have multiple kind of Cortex A cores, for example, on the NXP IMX8M+, in addition to like a hard DSP and a Cortex, an ARM Cortex M device. And then on the newest kind of NXP SoC, the IMX95, we have actually multiple Core M devices along with a Core A device. So essentially, like, we can start getting creative on how we want to take our application and how to distribute it across our single silicon. And that kind of starts unifying a lot of how we can think about how to distribute this workload and also how to manage these different controllers. So for example, if you were at Embedded World last week, you saw this robot from Cortex, and that had like basically an IMX8M+ SoC from NXP, and then you had basically the MCU responsible for the motor control and the actuation on the robot itself, and then the A core, the Cortex A ARM device that's on the same silicon was responsible for like the GUI, the interaction, and any sort of communication. So it's kind of an example of like, you know, what sorts of capabilities you have on this, you know, relative. It's a pretty small device, which is pretty cool, right? You know, as you can see, like somebody's leg is right there. So, you know, it's self-contained, it's pretty low power, et cetera, and physically small. Whoops. So yeah, so what are the advantages of having this architecture where you have microcontrollers and MPUs kind of all in a single piece of silicon? We have increased speed and reduced latency, right? So that's huge, right? We don't have to have, relatively speaking, for example, like between, let's say the ARM processors, right? Like you can use like actually direct interconnects within the silicon itself instead of having like SPI, UART, et cetera. These are, relatively speaking, slower buses. So you have much increased speed and reduced latency. OTA becomes a lot more simplified, right? So again, all you need to do is you have some piece of memory that you're writing to, and then you can just dump your binary into that memory that's responsible for where the MCU is operating out of, essentially. And so so you don't need to get creative. You don't need to you can start standardizing the MCU firmware update process, because if you're kind of all, let's say, on ARM cores, right, you have kind of the general framework about shared memory between a Cortex A, for example, and a Cortex M, and then they're sharing kind of flash locations that are specific, then the Cortex A can start marshalling the OTA process for the MCU for the Cortex M itself, for example. So that kind of framework or that kind of mentality led to the genesis of like this OpenAMP framework, which you can find a lot of documentation on as a starting point on the GitHub repo. There's multiple components to it, and we'll get into in a little bit. We have, of course, the OpenAMP library. And so the two main components of it are the remote proc and the RP message. They're the core building blocks of this particular library. So these two components actually were originally committed to the Linux kernel by TI. So the motivation for these implementations were essentially allowing communication from between Linux and TI RTOS, or what was then known as sysbio. So that was kind of the original motivation for TI starting this framework, and then it got picked up by OpenAMP, which turned into kind of this overall project and organization. And then they expanded what TI's work, what TI started, into a much more comprehensive and extensive library and framework. So this is kind of the overall motivation behind OpenAMP in general. So we have essentially a single kind of piece of memory that's essentially shared across, let's say, the different cores. We have the Linux and their application that's running on the Core A, the Cortex A, for example, and then we have, let's say, the RTOS and the bare metal implementations on the different Cortex M processes, right? So essentially, it's like this is all one big piece of silicon. And we're just kind of, we have to just be cognizant of how the different memories are distributed. So let's kind of dig into some of the actual applications and processes that are responsible or that kind of build up OpenAMP. So first we have remote proc. And what that's responsible for is to start marshaling, kind of writing or setting up the firmware on the MCU, for example. So one of the steps that it does is, one of the first things that it does is parses the ELF file. And so it's important for it to do that, so it's assured that it has the appropriate memory segments that are to be loaded. And this is going to be kind of important later on as how this ties into Zephyr. And so it loads the remote processor firmware, and then it also starts, essentially just kicks the MCU to kind of get it going. And then we have RP message, which is the actual communication mechanism between. So once you use remote proc to basically load the firmware and get it going on the Cortex M, for example, RP message comes along, and you can use that to essentially communicate between, let's say, your Cortex A MPU and your Cortex M MCU. And that's a very well-defined format on how this message exchange occurs. So you have this standard framework to communicate between these different cores. Two more kind of implementations of these overall mechanisms is, one is virt.io, so it kind of abstracts out the interprocess communication. And again, it uses kind of the shared memory region between the processors. And then we have metal, which is essentially the abstraction of the underlying OS primitives that OpenAMP uses to ensure, like, that all of the communication between your different processors are efficient, they're not kind of just hogging, they're not just inefficiently implemented. So kind of just looking at, now that we have kind of an overview of OpenAMP in general, we have remote proc, we have RP message, and then we have metal. So just kind of a quick overview of where they reside within Zephyr itself. So OpenAMP itself is an external repo that's part of the modules directory in Zephyr. And then so we have the Zephyr implementation of OpenAMP, which is essentially this resource table, which we'll get into a little bit. And then there's an example that I use as my starting point in Zephyr, which is under sample subsys IPC OpenAMP resource table. So that was kind of the starting point that I used for kind of this particular effort. And these are the relevant kconfig options. So config IPM is kind of enables the OpenAMP, the interprocessor kind of communication subsystem within the IPC subsystem within Zephyr. Config OpenAMP basically compiles the OpenAMP subsystem, and then the resource table config options essentially enable kind of this resource table, again, because that's one of the things that remote proc uses, is it verifies that your ELF file has that resource table entry to make sure that there is actually shared communication, that the MCU is aware that, what that shared resource is, so that it can communicate between the MPU and the MCU. So that's one of the first things that remote proc does, is when you actually, and we'll see how that loading process works, is very straightforward. One of the first things that there's like a kernel module on the Linux side that kind of checks and parses the ELF file to make sure that it meets certain requirements. If it doesn't, it kind of throws errors, but if it does, it essentially just starts the process of loading that into the MCU. And so one of the things that it does is it checks to make sure that this resource table entry is present in your ELF file. And then also, we need to make sure that, because we're kind of the slave in this, as part of the MCU, we need to disable the option to make sure that we're not the master in the OpenAMP configuration, because it defaults to a yes in Zephyr kconfig. And this is basically an example, in that same example that I referenced earlier. This is just the overlay for the board file that they're using, which is a STM32 part. And this is going to be useful later on. So again, we can see that we defined two things. We defined the IPC shared memory, right? We referenced that to a region of memory that's defined by the vendor, that is shared between the MCU and the MPU. And then the IPC itself is a construct that we can kind of create and use that for the communication itself. And then we can use like, which is typical in a lot of these multiprocessor systems, is we have this kind of mailbox configuration. So this was kind of the basis for what I did as part of this development effort. So kind of talking about the actual specifics of this project, and again, like I did it on different pieces of hardware because the hardware that was originally intended for the project was custom and proprietary. So I wanted to kind of see what I needed to do essentially to use like a commonly available like development board, and then see how that kind of takes me, how that progresses. So this was essentially it's the same sort of Xilinx product, but just on a different board by a different vendor. It's a Digilent Genesis ZU. It has a Zynq MPSoC, so that's essentially a quad-core Cortex A, and then a dual-core Cortex R. So it's not the Cortex M that we saw earlier in the earlier silicons. This is a Cortex R, which is meant for kind of real-time operations. So this is just a block diagram of the specific controllers within the MPSoC. So essentially, we have the Linux side that's going to be running on our Cortex A, and then we have our Zephyr is going to be actually running on the zeroth kind of Cortex R MCU, and then we need to define, again, like they call it an IPI within Xilinx land, like that's essentially going to be our IPC communication, and then the shared memory is what we define as a shared memory for the IPC as well, right? So we're going to need to define those in our device tree. This is again just kind of a block diagram showing from Xilinx's website like how this sort of implementation works. So on the Linux side, we have essentially the same sort of OpenAMP infrastructure, RPROC and RP message, and then underneath that is the virt.io kind of implementation to serve as the implementation of these two constructs. And then similarly on the Zephyr side, we're going to have kind of the same sort of thing. We have RP message, and then because remote proc is only on the Linux side, we don't have that on the Zephyr side. And then the virt.io is simply going to implement the RP message on the Zephyr side. So the goal is essentially we're going to create a Zephyr binary that's going to be resident, that's targeted for the R5, and it's going to be resident on the A53 RFS. We're going to load the firmware from the pedal Linux side, and then we're going to start it, and then essentially we're going to send a message from Linux to Zephyr, and the idea is that we should, the expectation is that we should get that message back on the Linux side as well. Okay. So how did I get started with this? So there's not a Digilent board in Zephyr at the moment, so I tried to find something that was close enough, and I found the Korea KV260 R5 board that is kind of present in Zephyr, and I use that as a starting point. And the first thing that I did was I wanted to make sure that my pinouts were correct, my clock configurations were correct, right? And I just got Blinky working, essentially. That's generally, when I want to use a new board or new kind of processor that's based on a newer board, that's usually kind of the first step that I do is just get Blinky working. And it's not kind of sufficient to just like, yeah, you know, like just eyeball it and see that it's blinking like at 1 second. Like you actually have to kind of generally like hook up like a scope and see, okay, maybe 110 milliseconds, 100 milliseconds, et cetera. That gives you confidence that, okay, your clock configurations are correct. The next step is just to get like UART working. So if you have hello world, that's higher confidence that your clock configurations are working because UART is a little bit more sensitive to kind of clock configurations, et cetera. So if your clock is off, you might be getting just garbled, data that's coming out of your UART. And so, part of this exercise also was, and we'll see later on, is like getting the Xilinx kind of tools like Vitis working with kind of Zephyr. So, typical flow is we have kind of debuggers, debugger configurations that are part of Zephyr, and you can use command line or you can use like Nordic Connect, and then you have like a debugger built in. This is a little bit different because there's no native kind of Vitis support in Zephyr, so kind of had to like get some like janky setup going, and we'll kind of get to that, like what that looked like a little bit, and then what the next steps are for that. And of course, the last step is to test, right? So once we have that working, we needed to or before this is once you have Blinky working, then we needed to make the appropriate configuration and modifications to get that working with OpenAMP, along with kind of the Echo example that's in kind of the Zephyr samples. So on the Pedal Linux side, I mean, it was pretty straightforward. We go through the Pedal Linux configuration. It's not the kind of focus of this talk. So all we need to do is enable the remote proc kernel modules and drivers so that we have that capability in Linux essentially. And then this is something that I needed to do, is to create the recipe in Pedal Linux to add the Zephyr binary. So the process was, I'd build the binary. I mean, it was pretty manual. Like, you build the binary, the Zephyr binary, and then you kind of plop it down into your RFS or your Pedal Linux build, and then create your RFS and then load that on the Xilinx side, and then kind of get going from there. So maybe there's opportunity here to kind of make this more integrated, so that you have like a automated process where you can just build the Zephyr binary and then kicks off like a Pedal Linux build to kind of embed that essentially, and then you don't have to like do more manual steps. And like I said, like, this was an important step to help me kind of debug issues that I was running into, is to use Vitis as a debugger. And so it was pretty manual. Like, I had to copy over a lot of the source files. There's like a bunch of different configuration steps in Vitis itself to kind of let it know like where the source files were, like where they were, how to set up the debugger itself, and then kind of reconcile the symbols within the binary within the source files. But, like, it was painful, but at the end of the day, I got like a pretty nice debugger where I could debug Zephyr code on a Xilinx kind of FPGA through their native kind of debugger, which is pretty nice. So kind of, let's say, so once things kind of started working well through the debugger, like how do we actually kind of load the binary and get it going, right? So it's pretty simple, right? You just, because the binary is resident on like a known path in our RFS, you just tell it like the file name without the extension. You just echo that to the sysfs entry, and then you just echo start, and it kind of kicks the tires. And then once, and it was pretty fascinating because I had the Vitis debugger set up, I could just set a breakpoint, and then like once I hit start, you could actually see like the breakpoint in main kind of kicking, like, okay, this is actually kind of working. So it's pretty nice. So kind of pivoting into some of the common issues that I encountered, and could kind of share some of the lessons learned with you. One of the first things that usually that did happen is just issues in loading and starting the firmware. So the kernel module itself, like, again, if you don't have the appropriate entries in your ELF file, it's going to throw an error. And one of the biggest reasons was you need to actually define this config option, like config OpenAMP resource table, is because it compiles essentially like resource table.c has an explicit entry for the resource table within your linker essentially. So then within your linker script, and then it adds that to your final binary. So that's kind of the one common issue that that I think a lot of people kind of run into. That's important to kind of make sure that's part of your board configuration. The other thing was, and I see this kind of common as well, is like, okay, you got the, like your binary is running, right? You can use different mechanisms to confirm that your Zephyr binary is running, but now when you start to communicate from the Linux to the Zephyr side, you get a seg fault, right? So like, why does that happen? So a couple of things to make sure that you're doing before, to make sure that you're actually doing to ensure kind of this doesn't happen. One is your IPC connected to the mailbox in your DTS, right? So sometimes that's not necessarily like a seg fault, it's just like nothing happens, right? Like I have a breakpoint where I have a callback set for when I get the message, but it never triggers, right? Well, do you have your mailbox set up to Zephyr IPC to make sure that communication is being received on the Zephyr side? You have to make sure that your SRAM, because in the normal kind of KV260 DTS file, the SRAM is not, it assumes like there is no other coprocessor. It just assumes that microcontroller is just by itself. And so you have to kind of update it to make sure that you're pointing it to the right memory location, to actually point it to the RAM is in the right kind of shared memory location that we saw kind of earlier. And then finally, did you make sure that your shared memory node is actually connected to your SRAM? So these are kind of the general 3 things that we need to make sure to ensure that we have kind of a successful communication between the multiple processors. So this is kind of like a detailed example of like what that looks like. So this RPU0 IPI is the interface, and then between like the IPC interface, which Xilinx calls IPI, and then here we can see like the mailbox that's essentially the entry between or the communication mechanism between the Cortex A processor and the Cortex M0. So this is the 0th MCU. And so all we need to do essentially is make sure that we enable that, and then in our overlay file, just ensure that we're setting this Zephyr IPC node entry to a reference to this particular mailbox. Okay. And then the other thing, like I said, is make sure that your SRAM location is correct. So the left is actually from Xilinx's kind of example on how they do OpenAMP with FreeRTOS. So essentially, we need to make sure that we specify these RAM locations in our Zephyr DTS and update that node appropriately. And then again, we have to make sure that our Zephyr IPC shared memory node points to the appropriate reference to like our SRAM node. And then the idea is that once you have these three components kind of all correctly configured, then you should have communication between the different co-processors that are resident on your silicon and on your system. So some of the next steps, of course, and I'm terrible at this, is to upstream, right? So add the board to like Zephyr, make sure it's there. It's a slight variation on the KV260, but again, I think having as much board support in Zephyr is pretty valuable. And then, like I said, I think it would be helpful for me to document the steps to get Vitis working with Zephyr, because I think that could be a pretty powerful tool for somebody else that's kind of using Zephyr with Xilinx products to be able to kind of step through using Vitis. So I think I have about 10 minutes for questions or comments.
Yes, we're at 12 minutes. First of all, thank you, Mohammed, for your presentation. Do we have any initial questions? I see one up in the front first.
Thank you for the talk. If I remember correctly, with STM32MP1, for instance, there were some concerns about OpenAMP and RP message throughput from the A7 to the M4. I think someone benchmarked it around 100K per second because it wasn't zero copy. You're always, managing this ring of shared buffers in SRAM. So if you want to do like zero copy transfers, is there some improvements that have happened in how that can be handled in OpenAMP, or is it better to just go below that and manage shared memory and signaling yourself?
Yeah, I'm not sure. Yeah, I haven't, this was kind of just a purely functional test. I didn't actually see okay, what the performance looked like. But yeah, I mean, it would be nice to see where that limitation, where that non-zero copy occurs across a different memory, and then see hey, is there an opportunity to just improve OpenAMP, and then maybe Zephyr could be leading the way to improve OpenAMP's performance essentially. So yeah, that's a good question.
So now you're booting the R core from the A core. You played around with the master function, so you first start Zephyr and then Zephyr starts your Linux kernel. So you have like a 1 second boot.
That's a good point, but how I guess so. You're assuming that the firmware is where would the Linux firmware and RFS be resident? You would have to kind of figure out a way to, it would be resident in Flash, right? And then you would have to instruct the Cortex A to, or would you, I guess I don't follow what that.
I'm implementing OpenAMP with Zephyr on the 9.5, IMX 9.5. So there we can use the boot fuses to launch Zephyr from the QSPI.
Right.
And then the idea is to implement the mode proc the other way around. But as a stopgap right now, we're just going to boot first Linux and then the other way around. But the notion that you have this fast RTOS booting, doing your PIMUXing, and then 10 seconds, 20 seconds later, whatever, depends on your Linux, right? That comes up later then.
Right. I guess I'm just curious, how, are you triggering the Linux boot from Zephyr?
Well,
Or is that the idea?
That's the idea.
Like-
There's now is a different bare metal method for it, but I was just curious because I now saw this master. It's like, oh, hey, cool. Maybe someone made that already.
No. I mean, like one of the things that like I was thinking about is like, okay, like if we kind of go back to like the robot, right, that I showed earlier, like one of the things like, okay, while Linux is booting, you could still kind of use the display interface to have Zephyr kind of display like a simple message so that, okay, while Linux is still booting, you have something to kind of inform the user like, hey, like what's going on. But yeah, that'd be interesting to see like how does, because I mean, if you're on the same silicon, right, like you're getting power for both, right? So like how do you kind of stage it so that Linux boots after kind of Zephyr? So,
Yeah.
and what would be, just out of curiosity, like where do you see that being like valuable?
So we're looking also at robotics. So the idea is that Linux is quality managed from safety critical perspective. So that can die, that can reset, that can crash. So, and then the control loop is running on the Zephyr side. So especially that robot, it will trip over. If you're going to use Linux, if you have Zephyr, you have uptime, it shouldn't fall over. Just you have power and you can run your safety critical or control loops
Got
there.
it. Well, yeah, cool. That's
Yeah.
Just to mention here, you can also start Zephyr with remote proc from Linux from U-boot. So they can start together. But yeah, I don't have an idea right now on how to start it from Linux to start from Zephyr.
Right.
They can start together, like from U-boot of Linux, you can, with remote proc, you can start the Zephyr core.
I guess it would be
Cortex
interesting to
runs
see like maybe you can have like an intermediary where you just have like U-boot like just sit there, and it's just waiting for like the remote proc from the Zephyr side to say like, okay, now boot, right? Because the firmware is already like it's there, right? It's resident on the flash. So okay, U-boot is just sitting there waiting for kind of, and then like once Linux boots, like okay, the Zephyr side can query like send a message and get a message back to see if it's successfully booted or not. Yeah.
Yeah, I've got a slight question or comment on OpenAMP, the protocol there. Are the messages fixed size? I mean, I think they are.
I think they're
And so-
well-defined, yeah.
Yeah, and so one of the challenges that we've run into is like, it's like you want a version of it that allows you to have flexible sizes for things like a network coprocessor sitting off on the that you're using OpenAMP to discuss, and so we end up. I'm saying we, my company, we end up with a custom version that's kind of close, and I'm not exactly sure why we didn't try to engage with the OpenAMP community to see if we can't get that up there. And I'm not even remotely familiar with the underlying change they did there, but it was dynamic versus fixed was a problem for certain types of applications.
Yeah, I had the same issue when I was talk yesterday about VirtIO, MMIO, that when you have that running underneath, you can run RP message on that, but that's fixed size and small units. But then next to it, you can expose a VirtIO network interface, for example. And then you use shared memory and next to RP message instead of on RP message.
Any more questions, guys? Okay, well, thank you very much for your presentation.
Yeah. Thank you.